Hi and welcome. So this talk today is going to be how we have approached developing a sports-based battle royale game for mobile. So I'm going to be talking about the issues we faced coming up with developing this from both a programming and an infrastructure point of view, and the solutions we came up with to overcome those. So the scope for today is we're going to talk a little bit about Stick Cricket, which is our flagship product, and the new game that we're developing is the next generation of that. I'm going to talk about the requirements that we identified for this project and evaluation of networking SDKs and sort of infrastructure services that we made. I'm then going to go on to talk a little bit about, or give a bit of an overview about the architecture that we developed for this, and then finally talk a little bit about Amazon Gamelift, which is a bit of a spoiler for the infrastructure evaluation, and then finally end on some Q&A. So Stick Cricket, the original Stick Cricket was developed way back in 2004 on Flash. So that's a long time ago. There have been a number of iterations and new versions since then, as well as spin-offs and new sports titles. And for our current portfolio across the board, we've got about 70 million mobile downloads, 2.5 million monthly active users, and 450,000 daily active users. And the last Stick Cricket game that we released, which was Stick Cricket Super League, is the highest rated cricket game on the App Store and the Google Play Store. Traditionally, Stick Cricket has always been in 2D. With our next product, we've finally made the jump into 3D with Unity. We've also, for the first time, introduced RealTime Multiplayer mode, which is going to be the focus of this talk. And we're currently in a closed beta, so I can't talk too much about it. But we are currently in beta with a Battle Royale mode, which is a 6-player version where each player is trying to outbat their opponents and stay in a series of ongoing overs with eliminations for low scores at the end of overs and eliminations for wickets. And then the player who survives to the end the longest wins, and then there's a pot of money. And the winner gets the biggest share with the rest divided out for other positions. So for this game, so we identified a number of requirements for this fairly early on. Players need to be able to compete in real time with each other. We need to support at least 6 players in a game. We need to support a large number of concurrent users. Certainly in the hundreds to thousands for our beta, probably more when we go worldwide. We want support for non-human players, so that's AI where we have maybe low server load or we failed to find a match for a player for whatever reason. We also wanted to be able to support test bots so we could load test our server. And it also needs to run well on low-end devices. For obvious reasons, India is one of our biggest target markets because they're absolutely cricket mad, and it's a huge market. And the devices there are obviously not quite as premium as some of the devices here, so you get a lot of lower-end Android devices around the sort of $150 mark. And it also needs to be able to run well in varying network conditions for similar reasons. So with that in mind, we made a few observations. One was that it's this sort of battle royale design, which you see, there's a few sports games that have come up with similar designs recently. It's not really fully real-time in the sense of an FPS that you would have on console traditionally, for example. So it's really what we kind of call like a semi-real-time game, or kind of like a turn-based game with real-time elements. So a lot of the time, I mean, cricket itself is very much turn-based, so each of the batters is facing a ball each turn and a number of turns per over. And then within that turn, there are real-time elements, so you can see your opponent's ball flights, you can see their scores updating in real time, and a few other real-time effects. But it's not a true real-time game. The other observation we made was that being a six-player game was that we wanted to go with a dedicated server model. So there's a couple of different server models. You can have peer-to-peer, which doesn't really scale that well, particularly with multiple players. You also have problems with sort of server integrity and cheating and so on, and having an authoritative server makes those problems a little easier to solve. With a dedicated server as well, it means that if one player's got a dodgy internet connectivity, then it's not going to affect every other player in the game. It's only going to affect that one user, really. The other thing, maybe slightly controversial at Unite conference, is that we don't really need Unity on the server side. So Stick Cricket's been around for a long time before we moved to Unity. And a lot of the logic is based off of sort of time and sort of pre-calculating results. And that it was important for us that logic and the feel of Stick Cricket stayed the same across the transition from 2D into 3D. So that logic is still pretty much the same, and it doesn't actually rely on sort of Unity physics or anything like that. We do use physics for effects and so on, but the logic itself doesn't rely on that. So now I'm going to talk about some of the networking APIs we looked at. We did look at a few more than what I'm going to mention here, but these are some of the big ones. So the first big one is Unity. We pretty much dismissed this one straight away. Again, somewhat controversial at Unite conference, but Unity don't really have a multiplayer API at the moment. They have UNet, which they've deprecated. And they've got a new transport API, which they're developing, which looks interesting, but it's currently in alpha, and it's going to be in alpha till at least the end of the year, possibly 2020 or something like that. So it wasn't good enough for us because we want to ship sort of in the coming weeks, months. So we had to look at other solutions. Photon is quite a well-known library that has been around for a number of years now. It's quite mature. It's got a lot of Unity integration. They also have their own cloud service that is integrated with it, which is quite appealing. Anecdotally, I had heard a few sort of troublesome stories with it, enough to sort of make us continue looking at other options. We also had a look at a number of open source UDP libraries. So these are libraries a bit like the transport layer that Unity is developing for their new API when it finally turns up. So that's basically like quite a low-level UDP networking library. So we had a look at a few open source and commercial ones, and this one here, LightNet Lib, seemed the most promising of all of those. It's open source. Unlike some of the open source ones you find on GitHub, is actually actively maintained as well, which is quite nice. It's cross-platform. It has a number of useful utilities, such as sort of serializers, deserializers, and sort of compressing packets and so forth, and debug utilities and sort of simulating latency and that sort of thing. And it's quite easy to extend. So yes, so ultimately, I think there's a slide missing here, but we, oh no, there's not. I'm getting ahead of myself. Sorry. The next step we wanted to have a look at was infrastructure. So we need to be able to host our server somewhere. So we looked at a number of options here. So the first option that we absolutely did not want to do was host our own server in-house. Stick Sports were quite a small to medium-sized enterprise, and we certainly don't want to be managing hardware. So that one was pretty rapidly dismissed. The step above that is cloud hosting using a service such as Amazon AWS or Microsoft Azure. Google also have offerings, and there are other companies with similar things. So it's better in the sense that you don't have to manage actual hardware. There is still some configuration and stuff you have to manage. There are also problems where they're not really designed for games. Scalability issues in terms of AWS, which we use a bit in-house at Stick Sports. They didn't have IP routing for UDP, which made that a bit of a non-starter for us. So that wasn't really where we wanted to go either. Unity have recently acquired a service called Multiplay. So it's what they call a hybrid cloud service, where you have bare metal or dedicated servers running, and then it's sort of topped up with on-demand cloud services. It's quite scalable. They claim to be quite cost-effective, and it was quite an interesting option that we looked at. Another option was Amazon Gamelift, which is quite similar to Multiplay. Unlike Amazon's AWS services, this one is actually sort of designed for games, and it is under the hood actually based on EC2, which is Amazon's cloud offering. But the layer above allows more sort of scalability. They've got various sort of game-related services as well, such as matchmaking. There's features to enable 24/7 service as well without any downtime, which was quite a nice big feature for us. And it allows you, unlike the sort of traditional EC2, it allows you to sort of spin up and shut down instances and fleets on demand, which is pretty nice. And it also has similar models with Multiplay, where you can have either on-demand fleets or you can have spotted instance fleets. So ultimately, we went with Amazon Gamelift. There's a few reasons for this. Ultimately, we decided that a lot of these services are much of a muchness, particularly Amazon Gamelift and Multiplay. And as a studio, we were already quite familiar with Amazon, so that was a big selling point for us. So we've got a couple of developers that are familiar with Amazon's IAM policies and so forth, and we didn't really want to have to do that onboarding with another service we weren't familiar with. And as an API, we decided to use LightNet Lib with that. So with Gamelift, you write your own server and you deploy that on a EC2 instance, or ultimately it's deployed on an EC2 instance. So we just needed a small sort of UDP layer, and that did the job for us. Okay, so I'm going to give an overview of the architecture we decided to implement. And I'm going to start, just before I start, I'm going to have a quick discussion about our actual project setup. So we use a slightly non-standard Unity setup at Stick Sports. So we actually have a dedicated Visual Studio solution that sits outside of the Unity project. And this is made up of .NET Core and .NET Standard projects. And then for the Unity-specific code, we actually have post-build scripts that actually copy that code across into the Unity project. So as slightly convoluted as that sounds, there are good reasons that we have for doing this. It gives us a bit more flexibility in terms of adding things like NuGet packages, adding different unit testing frameworks to what Unity offers, being able to reference projects with each other. I'm going to talk a bit about it in a minute, but our Stick Cricket server, for example, is a .NET Core console application, and we want to share code between the sort of logic layer that's going to run in the game, as well as on the server, and that makes that setup quite easy. So we've got a few core projects or modules in the Stick Cricket project. We have the tech networking project, which is pretty much just a small layer around UDP, or the LightNet Lib, sorry. We have Stick Cricket logic, which holds all the logic for our gameplay. So as mentioned, this doesn't really rely on Unity. And we have the Stick Cricket server project, which is just the console application that's ultimately going to run on an EC2 instance hosted by Amazon Gamelift. And then we have the Stick Cricket game project, which is the Unity project, which does all the Unity-specific things, so rendering the characters and playing sound effects, displaying UI, and all that sort of stuff, all the stuff the end user is going to see. So just a bit of a diagram for the server architecture. So at the bottom we have .NET Core, which it runs on. We actually have a number of tech projects, but the tech networking one is the one that's sort of relevant to this talk. And as I said, that's pretty much just a light layer over the LightNet Lib library. We have our Stick Cricket logic layer that sits on top of that, so that actually implements a lot of the game-specific network packets, as well as having all the game logic for running turns and overs and so forth. And then we have our Stick Cricket server program that sits on top of that, which is actually quite a small program and doesn't do a lot. A lot of the logic is in the Stick Cricket logic layer. On the game side of things, the diagram looks pretty similar, except for the inclusion of Unity. So really all these scripts actually live in, after the post-build step, these scripts live inside of Unity. So really Unity is kind of the bottom layer, but I've sort of set it up this way just to show that this stuff here is the same and it doesn't depend on Unity, even though it's within the Unity project. And then we've got the Stick Cricket game project at the top, which does depend on Unity and uses all the Unity APIs. So the packet class is kind of our lowest level class or most commonly used class in the networking project. So it's pretty simple, really. It just has an integer for a packet ID or unsigned integer and a payload, which classes derive from this packet. So in our Stick Cricket logic project, that's where all our game-specific packets are held, and they'll all have their own specific payloads, or some of them don't have payloads. So, for example, we've got a packet here that clients send to the server when they're ready to start an over. It just holds an unsigned integer. It's pretty easy. Some of the packets don't actually hold any payload at all, and they're useful for things where you just want a message that something has happened. The payload writer and reader are in the tech network project again, but they're just small wrappers over functionality that LightNetLib gives us. Managing that, we have the packet manager interface. This is really just to abstract ourselves away from LightNetLib a bit, because we want to give ourselves the possibility of, say, updating to Unity's transport layer in the future, or moving somewhere else. If LightNetLib stops being maintained for whatever reason. So it's pretty much just an abstraction for those purposes. So inheriting from that, we have a LightNetLib packet manager, which does a lot of the LightNetLib specific functionality. And from that, we then have a client and a server version, which are pretty much the same, except that the server one just listens to a port, whereas the client connects to a particular IP address and to a particular port. This is kind of a rough diagram of our client-server communication within the game. So it starts off just with the client sending a request to connect to the server, and then the server can reject that, or there could be an error. The server could have too many connections, but either way, it'll create a server response and send that back to the client. Assuming that's successful, the client then attempts to join a new game session in the lobby, and it sends a request to the server. The server then tries to find it a session and sends one back if it does. It also sends a few other messages related to players joining or leaving the lobby so that we can update the UI as appropriate. And finally, it will send a game data packet down to the game, which just has sort of information on the sort of deliveries that we've selected for that game and other game relevant information. Once we get into the game proper, we've got kind of a couple of loops. This whole section here is the main loop, and then we've got a couple of inner loops. So that's based on the fact that we can potentially have an infinite number of overs if players are tied. They keep going with overs there, and we keep going until someone's finally eliminated. And then within an over, we have multiple turns. So it starts off with the client sending a message to the server when it's ready to start the over, and the server then waits on messages from all the clients before it sends a message back to the client telling it to start the over. We then do a similar thing with the turns or the balls for that over. So the clients send a message when they're ready to start, and the server sends one back telling it to start. At this point, the client actually runs its own simulation of the game. At the same time, it is receiving and sending, when it's calculated it, ball strike information, round scores, and other sort of relevant information for the game. So this is stuff. These are the real-time elements where we sort of display these to each of the players as and when they come in. So, for example, players can see other balls flying off in their own environment, even though they're not sort of directly impacting their environment. It's more kind of sort of visual candy, I guess. There's other messages that go on as well, sort of latency updates and player state chains and so forth. And finally, when the player's eliminated, they disconnect from the server. So for that, we have there's a few classes that sort of are important there. We have an interface for a game creator, which is used in our lobby. So there's a server version of this and a client version of this. The server version of this basically tries to find players that are a match for a pending game, and it adds them in, and it sort of sends messages to the clients in the game of new clients that are joining or clients that have left, and so on. And then it is responsible for creating the final game or notifying the clients of a failure if something's gone wrong. And the client version pretty much just listens to those messages and waits for the game with all the data associated with it. That game creation result there then, as well as a success code, if that's successful, returns a instance of the game runner interface. Again, this has a sort of a client and a server implementation, as well as a kind of a base class that's sort of shared in that logic layer. So this just runs this runs the game. So there's not a lot here really. It's just a few events for different things happening, the overstarting, the turn starting, and finishing with results and so forth. And then a coroutine in the middle, which pretty much runs the game, and a few utility things. So those are defined then for the server and the client. There's a base class that does all the general game logic, and the server and the client side are then just doing specific things for sort of handling messages. So the architecture for that then, this kind of shows how some of that works. The client game runner and the server game runner both derived from that base game runner class. We then have this player view interface. So every game runner class has an array of player views. These player views are quite important, and I'm going to come on to that interface in a second. But we have multiple different types of players, and those are just classes that inherit or implement this interface. So we have, from the client's point of view, we have the human player view. So this will sit in the Unity game and deals with sort of physics and sounds and that sort of stuff. And it sends the player's score up to the server and receives information back. On the game side, you also have a remote player view, which handles receiving messages for other players within the game. On the server side of it, you have a network player view, which represents players that are connected in a game, and it receives messages from them, updates the game, and then sends sort of relevant results back to other players in the game. There are also other player types. We have an AI player view. We actually have a couple of AI player views that do AI-related code. In our test environment, which I'll get onto in a bit, we also have various test bots as well that inherit from that, so that our server actually thinks they're real players, but they're just sort of remote bots. So the player view, so the player view interface, as I said, it's pretty simple really. It's pretty much got this run round method here. On the client side, it does its logic for calculating the score. Unlike on the server, it pretty much just takes those and sends those back to the clients. On the game side, it actually then does a verification check, so it sends it up to the server and then waits for a result back, and the server will confirm that that result is correct or allowed. So the game runner, there's actually not too much point in looking at a few of those. Those are pretty much just, you've got a run overs method that runs each of the over, and then run over method runs each of the turns. This is the main sort of method in the game runner class. This just for each of the players calls a run round method. We've got a class there called barrier, which just basically is something that you can yield on until all of those things are finished. So there's a number of coroutines here for the run round, and just waits on all of those. The server program itself is pretty simple. Other than some quick kind of setup stuff, we just have pretty much a server that gets created, and then a while loop where we just continually update that server. So the server just has a server version of the packet manager, and it's constantly listening into requests to connect to the game, and then tries to connect games. So it'll spin up new versions of the game creator and add those to a list of pending games, or it'll find an existing one if one's appropriate. On the game side, we have a server interface. So this is another abstraction. So again, this is just this is sort of representing the actual server or service. So we have sort of an EC2 instance that sits behind this, and a Gamelift version. We've got a version that handles sort of running a local server as well. So again, this is just a bit of a wrapper really around the packet manager interface. So it allows you to connect and disconnect updates, send packets, and it's got a few other sort of helpers, so you can sort of send a packet and wait for a response as well. These are created then in a server factory. So we've got a few of these that are quite useful. The custom one's quite useful for just if a developer wants to spin up a server on their machine and just point it to a particular IP address. EC2, we haven't actually got Gamelift in here, but Gamelift is a new one that's come in since I've made that slide. EC2 is something we've used for testing and development. So we do, even though we're not using it for our final launch, it is useful for us for testing where we can just host it. And yeah, so that's useful. And these are all sort of toggleable, so you can sort of connect and disconnect from them in the game as well. It's all quite nice. It's all just hidden behind an interface. So it's quite easy to swap in and out. And again, it just stops us being attached too much to any particular API. So from a testing point of view, we've got a few test projects that we use for load testing our servers. It's pretty much just a case then of implementing a version of the game runner with classes that implement the player view interface, which are just test bots, and then just spamming the server. And we've got a few different bot types, some that are just dumb and just try and spam it as much as possible. Others try and mimic the user's behavior a little bit. We found that with a medium EC2 instance, so we never intended the server to handle that many players. With Gamelift, which I'll talk about shortly, you can spin up multiple server processes per instance and then have multiple instances and sort of scale that way. But for testing, actually so we're in closed beta. Our first closed beta, we did actually launch on EC2 because there was only a few hundred users. This was before we had Gamelift implemented. And again, because we had that sort of server abstraction, it was actually quite easy just to create an EC2 version of that. And then replace that with a Gamelift version when we had that implemented. But we found that a medium-sized EC2 instance actually handles 1,500 players pretty easily. There's very little memory usage, which is one of the benefits of the LightNet lib program, or library rather. And we're more CPU bound than anything else, but even then, we were sort of only using about 60% of the CPU, sort of playing. There's no noticeable lag. But it's not really a scalable solution, which is why we've gone with Gamelift. So yes, ultimately we wanted to use Gamelift, and that is what we've ended up adding in. And so it's worthwhile just having a bit more of an overview of Gamelift. So I'm not going to talk too much in depth about this because not everyone's going to want to use it. There are other similar systems available, but I'll talk about our experiences with it. So it's quite highly scalable in that you can spin up new instances and new fleets, and it'll do that on demand. It's got a matchmaking service, as I've mentioned before. They have a way of having 24/7 servers, so you can sort of spin up fleets and then have an alias to those fleets. And then when you've got a new version of your game, you can spin up a new fleet and just switch the alias over. And it means that players that are connected to the old version will just sort of slowly drop off and then reconnect to the new version, which, if they're incompatible, we'll sort of send them a message then saying, oh, you need to update. So that's pretty nice. Whereas some of these services, you have to maintain them, and there's a number of games that are in maintenance mode, which is a bit crap. It's also cross-platform, so it's got a number of integrations into various platforms like sort of Android, iOS, via Unity, UDK, etc. They've also got a really nice-looking real-time server API, which I've only seen recently. and it's in preview mode at the moment, but if I'd have known about it, we might have gone with. But they released that after we went with it. But that's kind of like a simplified version of a lot of this, so you don't have to set up your own server application. You can just sort of write C# or JavaScript scripts to extend sort of their server. This diagram is probably the best way of talking about Gamelift, and it was the most useful for me for getting my head around it. So you have your game client, which is your game running on a device, which then connects to a client service, which then talks to the Amazon Gamelift service. And then this service is what finds you a game session. Now, a game session can run on an instance of your, I shouldn't say instance, a server process. And you can have multiple server processes that run on multiple instances that run on multiple fleets. So that's kind of how that scales. So you talk to the Amazon Gamelift service, which finds you an appropriate server in an appropriate region based off of rules that you can configure and set via their sort of dashboard. This client service is quite interesting. So Amazon's documentation is famously not that great, and they tend to use game client service interchangeably and also just call it client, and they're actually kind of separate. So the way they recommend setting this up is that from your game, you ping the client service, which actually is what talks to the Gamelift service. And that client service could be anything from your own sort of server to a back-end service to some sort of serverless setup on Amazon or some other service. They also suggest that you can use it in-game and just have it as part of your game. That does work unless you want to run it on iOS or Android, in which case it doesn't. So we did have to go and after my first implementation of doing it that way, we had to set up our own service. So ultimately here we want to use AWS Lambda, which is what they seem to recommend, but it's not something that I'm familiar with, and we weren't able to get that in time. So we've actually just got our own little EC2 instance that just basically sits as a middleman in between our game and Gamelift. And the reason they sort of recommend doing it this way is just because ultimately your calls to the API are actually spinning up actual real-world hardware, instances and fleets and so forth. The idea is that if you've got it embedded in the game, then it's subject to possible sort of hacking and misuse. So having it in your own service means that you can add whatever security layers around that you need to. And I think that's pretty much it for me. Any questions? Hi.
I'm just curious about how you manage the persistence, the data layer. Like, where do you,
Yes.
what kind of database do you use?
So we're using we're using Firebase for a lot of our data actually. Gamelift does have some integration with some of AWS's services. We were already using Firebase for other projects, so it made sense just to sort of bring that over. But yeah.
So one big Firebase transactional, relational database?
It is a relational database, yeah. Okay.
Cool. And that's also on the Gamelift?
No, so Firebase is Google's offering. Amazon do have their own, obviously, databases and so on, and there is sort of quite tight integration between.
What kind of throughput and bandwidth do you see on there, on your database side?
I don't have the answer to that question at the moment. I can certainly find out for you. Anything else? Hi.
Yeah. The Gamelift fleets, is that like a serverless logic thing, or is that like reserved instances?
So you can either have dedicated fleets, or you can have fleets that sort of spin up on demand.
So
So
spin up, it's not like a per request serverless thing?
no, I mean you can spin them up per request. So the Gamelift API does allow you to spin up fleets as well as just ask for instances. Normally you just sort of request a game session, it will spin up an instance or something for you if it needs to. But the APIs are quite flexible. You can do a lot of stuff with them actually. Anything else?
No,
Hi.
sorry, I've got a
Sure.
question. I love your the way you've structured it. In fact, I've done something a bit similar.
Yeah.
And I wanted to ask you, what does your build pipeline look like? Given that you've got Visual Studio,
Yep.
solution, bunch of projects.
Yeah.
Like I'm trying to automate it as much
Yeah,
as
yeah.
I mean, I hate
Yeah.
building.
Yeah, of course.
But I find it really difficult because I'm compiling Visual Studio
Yep.
files, copying them across.
Yeah.
Sometimes I find that Unity doesn't play nice with all the source
Yep.
code. You know, some things, like you said, Android, iOS don't like
Yeah.
them. What does your build pipeline look like, and how do you manage that process?
So we use MS build tasks. So we've got our own, it's probably a little bit out of scope, but we've got our own build tasks that use Microsoft's SDK, and then those work cross-platform, so they'll deploy on iOS, OS X, Mac OS, sorry, these days, Linux, Windows, whatever. So pretty much, yeah, you just compiles the projects in Visual Studio, so you just hit build or run .NET build from the command line, and the post-build scripts will then just copy basically all the files into Unity itself.
You're copying scripts across,
No DLL.
not DLLs.
Some of the projects are set up in a way that they copy DLLs across if they require those DLLs, but it depends on the project. So like the LightNet lib, so the tech.net working one will copy the LightNet lib DLL in if it's updated. But yeah, agree with sort of pipelines and stuff, and we're all sort of set up with CI and whatever, and Jenkins and all that sort of crap. So.
How would you recommend a small scale, like someone to? Is it feasible to set it up that way?
Yeah, it's so I worked at another company before which had a similar setup to that, but they were more Windows focused. So this is actually using .NET because it's all using .NET Core, and the build tasks are all sort of cross-platform. It's quite nice that it works across. It's actually quite simple to set up. I mean, if you only care about Windows, it's quite easy to set that up as just editing the project files anyway. But it's a little bit more work involved if you wanted to work cross-platform. But there's a few things to iron out. But yeah, I mean, that could be its own talk, to be honest. I can chat to you more about it afterwards if you want. Anything else? Okay. Thank you very much.